Hello everyone, it's Anuit Kumar. Welcome to Key Concepts. In today's session, we are adding few more points in how to select the initial state detection threshold values. First, before starting this session, we are going to first recall what are the key concepts that we have discussed in our last lecture, and then we continuing and adding some more point on this setting, and then we will discuss what are the major key issues that we are facing while selecting the wrong values and what are the different observations that I have faced while doing these type of activity or tuning the motors. So as we have discussed how these devices basically sense the back EMF section. While sensing, we determine that the two states whether the motor is spinning or it's a stationary, and when it's when it's running, then it will justify like how it's running in a forward direction and how it's running in a reverse direction. That this particular thing that we are going to do in this session. So before that, like it has a phase-to-phase comparator, and that will sense the phase difference between the two different phases of back EMF, and based on that it will, if the output is having a phase difference, that it means that motor is running in a forward direction or reverse direction. If the phase difference is a phase, like you can say the reference will be zero, comparison of the two different phases. If the phase difference is zero, it means like a motor is not running. If motor is not running, we need to go ahead for the PSD setting or align and go setting, and then we go for the startup setting. So that's the sequence that we are going to follow. So all those the details we have already discussed. If the motor is in a running condition, then condition will be different, like it's already have a back EMF section. So don't get confused running what actually it means. So I already have discussed like in the last lecture, like if a motor is in a running condition, assume motor is running in a 230 300 rpm, let's assume it case, and suddenly what you have done, you just switch off the fan, then still motor is running, like next 3 to 4 seconds it will running in a lower slowing down. So let's some condition 2, when the motor is in a still running condition and you already switch off the fan, so still running with the 100 rpm. So in that condition, if you are on the power supply or on the fan, in that condition, that particular rotation without any power, giving a power supply, still motor is rotating, that is the condition we are considering as a spinning. Don't get confused. If motor is power up, then it's running. No, when your inertia is there, that's why your motor is running, and that particular running condition, it means motor is in a rotating condition. Then we have a back EMF, and we are sensing that particular back EMF. Based on that, we are executing this particular state. If your motor is spinning, it means it can provide you the rotor position while providing you the back EMF value, and that's we are different we can justifying by sensing the zero crossings. If we have zero crossings, that we can assume that we have a back EMF value, right? In that case, you don't need to execute the PSD setting. What you need to do, you need to just start the motor. You can say that it's just go for the startup setting. We don't need to start the motor with the IPD or PSD setting, right? If you selecting the different ISDT value, then how it affects your motor tuning? That's the important. That's a very important point. So sometime once we start the motor and we have selected the very long time duration, in that time what we have physically see, motor start with the delay. Once you switch on the motor, it will wait for 1 second or 2 seconds. If you selected 3 seconds, then it will wait for 3 seconds. So all those graphs that we have discussed, okay. Then we have discussed what are the two different criteria to select the different ISD settings. So initial state detection threshold setting. So what we have observed that if your motor velocity constant is very higher, and then you need to select the longer time duration, and if your motor velocity constant value is less, then you have to select the shorter time duration. Why we are doing this? Usually when your motor is running in the lower RPM, let's assume two different cases. First, the motor having a very high RPM and the motor having very less RPM, and the another point, like your motor velocity constant have a lesser value. At a higher RPM, you might get a very good back EMF sensing, and that will allow you to switch your motor to the closed loop operation. But when your motor is in a running condition at a very less RPM or a lower RPM, in that time, if your back EMF value is very less, in that time you are not able to find a proper back EMF value. You're not able to sense your proper back EMF value if your motor time, or like you can say the ISDT time duration is very higher. Okay, so in that time, in that case, you need to select the lesser time duration. Hope you understand. And the same way, if your motor having a higher velocity constant value, it and at a lower RPM, it has a sufficient back EMF value to switch your motor to the, you can say, in a closed loop operation. So what actually it means, like the basic criteria that we have already discussed, like if your motor having lesser, then we have to select the lesser time. If your motor is having motor constant value is higher, then you have to select the higher time duration. Okay. Then another criteria that we have discussed, the motor inertia. The motor inertia, what actually it means, if your motor is very heavy and it's in a rest condition, it will allow some time to start the motor. Okay, so what you have to do, if your motor inertia value is very higher, you need to provide the lesser time. If your motor inertia is higher, then you have to allow the higher time duration, usually in a second. If your motor inertia is low, then you have to provide a lesser time duration. Okay, so this is the few addition that I have discussed in our lecture. So what actually happens if your motor, this is the how the comparator works. Usually you have a like this is the vector representation of the three phases, and these are two different values. So usually it like 30-degree leading, and this is the 30-degree lagging. Okay, so resultant difference between these two different voltages, like UW and UV. So the actual difference between these two angles is actually 60 degrees. So what you're seeing there, so UV is like you can say it's a start from zero horizon, or you can say crossing the horizon, zero crossing, and this first is like zero crossing or a first horizon is shifted by 60 degree. So based on these two factors, like how what we have discussed, like a stationary condition, there is no phase difference. But if it's have a phase difference, but running in a reverse direction or running in a forward direction, how these devices, how is going to justify the point, like whether it's actually running, either running in a reverse direction, either running in a you can say in a forward direction. If it's running in a reverse direction and you give the command in a forward direction, so what you need to do, it will stop first and then it will start in a clockwise direction or which direction you have selected. So this is the basic, you can say, criteria to first need to sense the position, whether even though it's spinning, but spinning in which direction, it need to justify first. Okay, so how it's going to do this? So what we know, like spinning in forward direction, if the, you can say, the UW or a UV, if the UV comparator is 60 degree leading the output of UW comparator, then motor is in a forward direction. Okay, and if your UV comparator of like whatever the comparator that we have is 60 degree lagging the output of UW comparator, then the motor is spinning in a reverse direction. Oh, okay. If neither of comparator output give the changes the amount of time, then it spins as stationary. The same concept that we have discussed. The rotor position and the speed can also gotten from the comparator output, which is start the motor when it's spinning in a forward direction. Okay, so hope you understand what I'm trying to say. If your 60 degrees leading, in that case motor is in a station, like you can forward direction is spinning. If you're lagging, if your first phase is compared to the second phase is lagging by 60 degree, then it means that motor is running in a reverse direction. Okay, hope you understand. So even though your motor inertia is higher and like or you can say the higher in the sense it's like ceiling fan, it's not I we can say like it's very much higher, it's someone what middle value. So in that time if your delay is very higher and you keep that's not it looks annoying to you, then what you need to do, you need to reduce the time of that particular setting. Okay, to some extent you not able to face a delay, in the same time it will not fail to start or it will not go for the jerk start. Okay, the first point, if you face any delay in the startup, what you need to do, you need to reduce the time duration of your ISD setting. The another point, fail to start at the lower RPM. So this is the initial condition when the motor is in a stationary condition. Then what it does, it first you go for the startup setting section, then it will go for the you can, so first it's go for the ISD setting, so it will have some delay, then it will go for the PSD setting, then it will go for the startup setting, right? So if you selected a very high value of delay, let's assume this, if you selected very high value of delay, then till that particular time duration it will stop. So what you need to do, you have to select the less ISD setting value, less ISDT setting value, and then this particular delay time will be get reduces. Okay, but the same time you have to check that whether it's perfectly starting or not. Okay.